second order differential equation. So you have x squared y double prime plus xy prime plus x squared y is equal to 0. Now things are aligned where I can use this method of Frobenius. Okay, so if I were to divide this equation by x squared, okay, so this is going to come down to, okay, so you have y double prime and for the middle term this is going to get a little bit redundant, but do want to mention, so you have x over x squared times y prime, and we have plus x squared over x squared times y is equal to 0. Now with the method of Frobenius, your setup is going to be, you have y double prime as the first term, and with the y prime term your coefficient is going to have x in the denominator. So we have x over x squared, so this is going to become 1 over x. Okay, we have times y prime, and now for the last term, for the variable term, okay, we have x squared at the bottom, so I'm going to leave x squared over x squared as it is. Okay, and now with the method of Frobenius, okay, so the numerator, the first order derivative term, okay, that's going to be your p of x. So right away you have p of x is equal to 1, and the numerator, the variable term, x squared, that's going to be your q of x. And taking what we have and evaluating p naught, well, guess what? It doesn't matter what value of x you plug in, because p of x is already baked in as 1, so p naught is already going to be at 1. And for q naught, okay, so you're looking at q of 0, and since q of x is at x squared, so we're looking at 0 squared, which is equal to 0. Okay, so you have an algebraic setup. Okay, and now entering the scene, okay, we have with the method of Frobenius. Okay, so you have this algebraic equation. Okay, so you have r times the quantity of r minus 1, and we have plus p naught r we have plus q naught, okay, is equal to 0. Okay, so we have again p naught is at 1 and q naught is at 0. So you have r times the quantity of r minus 1, and with p naught equal to 1, so you have plus r. Q naught is negligible. So now I have r squared minus r plus r, which will go out. Okay, so we have r squared, okay, is equal to 0. Okay, so we have a repeating root with r. Okay, so our r of 1 in this case is equal to 0. Okay, so we have r of 1 is equal to 0, and that is from taking this equation and applying the method of Frobenius. Okay, now in the case of what we have with y, okay, with the method of Frobenius. Okay, so we have notes used. So we have from the setup, okay, so you have y, again, so you have in general terms cases, you have x to the R1. And again, have times the summation as n goes from 0 to infinity. Again, we have a c of n times x to the n. Okay, and since R1 is equal to 0, okay, so there's no degree that's going to be added to x to the n. Okay, so that's going to be locked in at c of n times x to the n. Okay, now just for what we have in this setup, so in the original equation, okay, so we have again, so you have a y term, the first order derivative y term, and also second order derivative. So we're going to take for y. Okay, so we have with the initial setup. Okay, so we have for y. Okay, so again, I have, again, as n goes from 0 to infinity, and we have a c of n times x to the n. Okay, and among your first terms, okay, so if n is 0, we have c naught, and again, x to the 0 is going to be 1. Then we have plus c1x plus c2x squared, and I have plus c3x cubed. Now for the first order derivative, okay, so taking the first order derivative, okay, now we have with the algebraic expression, okay, so you have c of n times x to the n, first order derivative. Okay, we have n times c of n times x to the n minus 1, and taking the first order derivative of these terms. So c naught, the derivative goes out, so we have the first c of 1 times x. Okay, the first term is going to be c of 1. Then we have plus 2 c2x plus 3c3x squared. Okay, so in this particular case, all right, so you say we have n going from 1 to infinity. And again, you have the summation of ncn times x to the n minus 1. And for what we have in the case of the second order derivative, okay, so I got n times n minus 1 times the quantity, so you have c of n, and this will be 2 times x to the n minus 2 power. And we have with this, okay, so c of 1 now goes out, so we have 2c2, and we would have 6 c of 3x. Okay, and if I were to continue, so I got like 1 times 2, 2 times 3, 3 times 4, so that's going to be 12 c4x squared, and so on. And we have with the limits. Okay, now if I start out at 0 or 1, you're still correct in a sense, but those terms would become negligible. So to get the first term to be non-negligible, okay, you have the lower limit. Okay, you have going from 2, starting at 2, going on out to infinity. So this is the general representation of what we have for y, y prime, and y double prime. And so now, taking what we have with the series, okay, now again, the original equation, again, we have x squared y double prime plus xy prime plus x squared y is equal to 0. So if we substitute in, okay, the series terms, okay, so you have, again, so you have our x squared y double prime Okay, so you got x squared times y double prime, and for x times y prime, so I have a y prime, so I have c of 1 plus 2c2x plus 3c3x squared, and so on. Okay, and you have plus x squared y. Okay, so putting in for y, so you have c naught plus c of 1x plus c of 2 x squared okay, and again we have is equal to 0. Okay, and now looking at what we have in the mix. Okay, so I've got in the layout, so just multiplying by x squared, so I have 2c2 x squared plus 6c3 x cubed plus 12c4 x to the 4th Okay, we have distributing x squared okay. Now it's going to turn out that quite a few terms are going to go out, because looking at what we have among the items. I'll just copy this. Okay, if you notice, okay, we have okay, so you have the lowest degree term at the front, have an x squared, we have x, we have x squared. And if you notice, okay, we have an x squared, we have the coefficient subscript, we have 2 and 0. But the lowest appearance of the odd subscripted constant, then we have a c1x, and there is no first order x term that's going to be joined with this. And guess what? Since what we have here, since we have CO1 times x, since there's nothing that's going to join with this, your first constant is going to be at 0, or CO1 is going to be at 0. And we have, and in terms of anything else, that CO1 would be mapped with, if I were to continue to have CO1 reappears as x cubed, guess what? We have C of 3 x cubed. So there's going to be a domino effect. Because odd coefficients will be joined with other odd subscripted value coefficients. Okay, so you have, say, got like 6c of 3 plus c of 1 is equal to 0, at least from this particular part. And since c of 1 is equal to 0, guess what? C of 3 is also at 0. Okay, so anything that is odd value, okay, in the subscript, okay, that is going to lead to negligible constants. So C1, C3, C5, C7, and so forth. Okay, those are going to go out. Now, for what we have left over, okay, now for the constants that are not negligible, and those are going to be what we have with the even subscripted terms. Okay, so for what we're going to have in the mix, okay, so if I were to combine what I have with what we have in x squared, okay, so it looks like combining what I have here. So it's like we're going to have 4c2x squared we've got 2c2x squared plus 2c2x squared, so I have 4c2x squared, and I got plus c naught x squared is equal to 0. And if I were to continue, okay, so you got in x squared, and you'll have also in x to the fourth okay. So just combining like degree terms. Okay, so you have, let's see, not there this end. Okay, so we got, it's about 4, 12. Okay, so 30. Okay, now for what you have in combining terms together, and we'll have a relation between c of 2 and c naught. Okay, so we have that c of 2 is equal to negative c naught over 4. And correlating what we have with c of 4 and c of 2. Now we're going to have 12c4 plus c2 is equal to 0. I'll go ahead and say that we have c of 4 is equal to negative c of 2 over 12. Okay, let me check. C of 4. You know what? Got a little bit ahead of myself. That should be 16. My bad. Negative c2 over 16. There we go. And if I put this in terms of c naught, okay, what's going to happen here is I'm going to have negative times negative. Okay, it's going to be a positive. So I have c naught over 64. And for c of 6, I'll take this one more time, so I have negative c of 4 over 36. And what's going to happen here, so we have a negative times positive is a negative, so this would be a negative c naught all over 2304. Okay. And what I'm going to do here, okay, is I'm going to put this in terms of this particular Bessel expression as much as possible. And I'm going to establish, okay, some of the factorial notations. And so we have, for like negative c naught over 4. What's going to happen here? Okay, so you're going to have like the negative of c naught, and this will be all over 2 squared times 1 squared. Now for c naught over 64, okay, so we have c naught, and now if I'm working with base 2, okay, so you notice we have with this expression, okay, so we have 2 on the denominator, so we fixated on the exponential base 2. Okay, now in terms of, okay, now 16 is 2 to the 4th, and again 64, okay, that is 16 times 4, And so I'm looking at, in the layout, so I'm looking at 2 times 1 squared. And then we have with the third term, so you have negative C naught. And we have a pattern. So you have the subscripted C term, you have it 2 to the 6th. And now for 2 to the 6th, so we're looking at 64. And guess what? 64 into 2304, that's going to be 36. And guess what? There's going to be a pattern here. So you have 3 times 2 times 1 to the 2nd. Okay, so you have 1 factorial squared. And we have C naught, okay, and we have all over, you have 2 to the 4th, and 2 times 1, so you have 2 factorial squared. And then we have negative C naught. So negative C naught. Okay, so we have 2 to the 6th. And we have now 3 times 2 times 1, that's going to be 3 factorial raised to the 2nd. Okay, so there's going to be a pattern. Okay, so you have even subscripted values. Okay, so you have like C of 2, okay, this will be your C of n. And if you notice, you have alternating between negatives and positives. Okay, so let's say you have like negative 1 to the n over 2. You have C naught. And again, we have with the layout. Okay, so you got 2 to the n, and have n over 2 factorial. Okay. And again, if I get rid of the fractions, okay, so if I let n be equal to 2k, so if we let n be equal to 2k, so we have C of 2k. So we have minus 1 to the k, C naught, and this will be over 2 to the 2k, and I have times k factorial. Okay, so this is going to be our C of 2k. Now, once again, going back to what we had in the original establishment, okay, with y. Okay, so y going from 0 to infinity. Again, have C of n times x to the n. And again, letting n go to 2k. Okay, so as k goes from 0 to infinity, okay, so I have C of 2k times x to the 2k. Okay, I got C of 2k equal to this statement, and let's say if I just move the constant C naught out to the front, So I have k going from 0 to infinity. And I have a -1 to the k. And I have times x to the 2k. And again, I have all over 2 to the 2k. And I have times what is going to be k factorial. In fact, k factorial. You know what? I'm going to do this additional wraparound. I overlooked something. So I have n over 2 factorial, and that is going to be squared. Okay, so this is what we have for C naught in case you have, again, so you have y equal to C naught times the summation. Okay, so you have -1 to the k times x to the 2k divided by 2 raised to the 2k times the square of k factorial. Okay. Now, again, we were dealing with, okay, now the degree of r was at 0. And what I'm going to do is I'm going to apply treatment to the k factorial. Okay, so I have -1 to the k, x to the 2k. We have all over 2 to the 2k. Now I'm going to do it here instead of the square of k factorial. I'll show you why I'm doing this. Okay, so you're going to have, I'm going to separate into separate factorial terms. So you have like k factorial. We have k plus 0 factorial. And as we narrow it down, what I'm going to do is that, okay, if you notice for the Bessel function of the first kind of order p, okay, had this variable expression at the end that correlates what we have in degrees of x and 2, x in the numerator, 2 in the denominator. So I'm just going to mention, okay, so we have for the part that which we have for x to the 2k and 2 to the 2k. So we're just going to sandwich these together. So you have x over 2 to the 2k, just to line it up in the form that we have for the general expression of the Bessel function of the first kind of order p. Okay, so we have in this particular case, right? So I have C naught times the summation as k goes from 0 to infinity. So again, I have -1 to the k. Again, so I have k factorial times k plus 0 factorial, and then for the x to the 2k and the 2 to the 2k, we have in this ratio. Okay, so I have x over 2 raised to the 2k, and so for what is going to happen in this particular case, and we don't have to worry about the constant so much, but for what we have, so you have a constant times this particular summation, and what's going to happen here is that this is going to reduce to our Bessel function that we're going to have. Your p is going to be at 0. Okay. So again, you have for your for your Bessel function of the first kind of order P. Again, this is your algorithm. And again, if the order, okay, P represents the order, and the order is 0, that's fine. -1 to k, K factorial, if P is at 0, and if P is at 0, you have x over 2, simply 2k power. So that'll be the result in this particular case. So that'll be your solution where you have the Bessel function of order 0. Okay. And now, just another case, and we'll be looking at kind of a taking a sampling of what we have with Maple. And let's say that if we have, so I'm going to go with this one, number 49. Yeah, we'll go with the binomial expression on this one. Well, let's say we have another equation. Okay, and we'll say we have okay, say we have x squared y double prime, and we have plus xy prime. And we have plus x squared minus 4 quantity times y is equal to 0. Okay, so if we divide, once again, this equation by x squared, okay, so we have y double prime plus x over x squared y prime and plus the quantity of x squared minus 4 over x squared y is equal to 0. Okay, so again, with the method of Frobenius setup, I want to leave the fraction alongside the y prime. I want to leave the denominator in terms of x. Okay, so just taking a little rewrite, so we have y double prime plus 1 over x times y prime plus, once again, you have the quantity of x squared minus 4 all over x squared times y is equal to 0. So little history repeating, at least from the first part. Okay, so your p of x is equal to 1. Okay, but your p naught again, you have p of 0, so that is again going to be at 1. Now for your q of x, again, your q of x is equal to x squared minus 4. And now we have for q naught, so you're looking at q of 0, and so you have 0 squared minus 4, so q of 0, or your q naught, is going to be at minus 4. So we have entering what we have with the method of Frobenius. And so we have, in this one case, so we have r squared minus r, and p naught is at 1, so we have plus r, and q naught we have at minus 4. Okay, so we're down to the difference of squares. Okay, so we have r squared minus 4 is equal to 0. Okay, and r squared is equal to 4, or you could factor, so r, you have it plus or minus 2, and again, we're going to go with a higher root value. So in this case, all right, so with r1 being the higher root value, we'll have the r1 is equal to positive 2. Okay. So we choose that one. Never choose the lesser if you're looking at trying to establish a Bessel function of the first kind. Okay, so and we have just taking what we have and establishing. So we have r1 equal to 2. And again, this time r1 is equal to 2, so I'm just going to take what I have here. So x to the r of 1, you have x squared times the summation, again, as n goes from 0 to infinity. We have c of n times x to the n plus 2. So c of n x then, and we'll go ahead and say. Yes, I have x squared times c of n times the summation. As n goes from 0 to infinity, so you have c of n times x, and now I can say it that had the summation as n goes from 0 to infinity of c of n times x raised to the n plus 2 power. Okay. So this is going to be our general setup. Okay. Okay. So for what we're going to have here, so n is at 0 and x is to the 0 plus 2 power, we're going to have for our first term, we're going to have c naught x squared, and then we'll have c of 1 x cubed, and c of 2 x to the 4th. I can just keep going where the superscript is going to be 2 more than the subscripted. Okay. And for what we have in case the first order derivative. Okay, so we have n plus 2. All of n plus 2 times c of n, and this will be times x raised to the n plus 1 power. We can always check for the consistency. So the first order derivative, so you'll have 2c naught x. And you have plus 3c1 x squared. And you have plus 4c2 x cubed. And plus 5c3 x to the 4th. Okay. And this time around, okay, if you notice the first subscripted value we have is 0. So you're still going from 0 to infinity. Okay. Now for the second order derivative, Okay, so I have n going from 0 to infinity. Okay, so I'm now looking at n plus 2 times n plus 1, or vice versa. And so we're going to have c of n times x to the n. Okay, so first term we're going to have 2c naught, and then we'll have 6c of 1 times x. That's 12c of 2 times x squared, and so on. Okay. Now, in looking at what we have on the basis of the establishment from our equation started out with. Okay, so again, that was okay. So I have in the mix. Okay, so I have, once again, so I have x squared y double prime. And I think I'll do here. Okay, so I have x squared times this set of terms. And I have plus x times, okay, y prime. Okay. And if I were to distribute, okay, so I'm going to have x squared again for what I had in y. Again, we had that minus 4 part as well. Okay, so I have all these distributions involved. Okay, again, so you have x squared times the series from y double prime plus x times the series from y prime. Then you got plus x squared times the series from y, as well as minus 4 times the series from y. Then we have set it equal to 0. And if we take these terms, and I'm just going to kind of condense what we have here. Okay, so we wrote this down. Okay, so we're going to have, first of all, if you combine like terms together, so you have 5c of 1 x cubed plus 12c of 2 x to the 4th plus 21c of 3 x to the 5th and I'm going to have plus c naught x to the 4th plus c of 1 x to the 5th plus c of 2 x to the 6th and so on is equal to 0. Okay, so just for what we have in the lineup, okay, notice we have close to each term we have an x cubed, and there's no other x cubed term there, so it's going to have x to the 4th, 12c2 of c naught, and that's why the triad the next pairing, okay, x to the 5th, about 21c of 3 and c of 1. That's why c of 1 is already negligible, so we had the same kind of domino effect. Okay, that is going to reappear. Okay, so you have your odd subscripted value constants are going to be negligible. Okay, since there's no other x cubed term to be mapped with 5c of 1 x cubed, so c of 1 is going to be equal to 0, and that's just going to carry over to the others. Okay, and so we'll have c of 1, c of 3, c of 5. And in terms of the constants that are non-negligible, so those can be the even subscripted terms. Okay, so we got for this, in case you had 12c of 2 x to the 4th plus c naught x to the 4th. And I was going to put this in terms of just the coefficients. They had 12c2 plus c naught is equal to 0, and you would have next in line, okay, so you had 12c2 plus c naught is equal to 0, and we would have next item, this would have been 32c of 4 plus c of 2 is equal to 0. Okay, now expressing what we have for c of 2 in terms of c naught. Okay, so you have negative c naught over 12. Now putting c of 4 in terms of c of 2. I'll get too far ahead. I do want to put it at c of 2 in. Okay. Okay, so you have c of 4, okay, have equal to the negative c of 2 over 32. And in terms of c naught, so we'll have like negative 1 over 32 times negative 1/12 of c naught. Okay, so you have c naught over 384. Okay, now in terms of the sort of the breakdown, okay, so you have so I want to work with the base 2, and what's going to happen here, okay, now I'll show you, okay, a bit of a pattern that's going to reoccur. So you got for c of 2 in terms of c of naught, so you got negative 1 to the 1st, c naught Okay. Now I want to maintain a balance, okay, working with base 2 and also with factorials. of natural numbers. And guess what? Okay. Now, I was kind of tempted to say 2 squared times 3. Well, 3 is not a result of factorial value from say that 3 is not a result of the product distinct natural numbers other than just 1 or 3. But if I put this in terms of 2, let's say 2 to the first, 2 going to 12 6 times, and 6 is 3 factorial. Okay, so I have like 2 to the first times 3 factorial. Okay, now for what I have in terms of, C of 4, we have positive value, so we have -1 squared C naught. Okay, and if I maintain the order, okay, so if I have like 2 to the first, okay, half the degree of the subscriptive value, so I'm going to have, in this sense, I'm going to have 2 squared, and for what I'm going to have in this particular layout, okay, let me do it. I'm going to do it like this. I don't want to get too far ahead. Let me expand this first expression on out. I'll show you what I'm doing here. Okay, so I got 2 to the first times 1 factorial times 3 factorial. Okay, now and let me mention, if you recall now, the R of 1 we were using was equal to 2. And then we have P is equal to R of 1 is equal to 2. Okay, so you're going to be looking at, in the pattern, we'll have like K, like once you get back to the decimal notation, we have K factorial and what's going to be K plus 2 factorial. Okay, so you have 1 factorial times 3 factorial. And guess what? We have 384. Okay, so you have 2 squared, 4, we're going to 384 96 times, and for what we're going to have in this particular case. Nope, you know what? It's not going to be 96. Let's see, it's got 2 cubed. 2 factorial times 4 factorial. 2 factorial is 2. 4 factorial. Okay, that is going to be 24. 24 times 2 is 48. 48 into 384 is going to be 8 times. So that's going, and 8 is going to be 2 to the third power. And if I were to go out to, let's say, C of 6, what's going to happen here is that this will be like negative C of 4 over 60. Okay. And so what's going to happen in this particular case, you're going to have negative C naught we're starting to get into large numbers here. Yes, 23,040. Okay, so now we're going to have negative 1 cubed C naught. And see, now we have 3 factorial, that is 6 times 120. Yeah, it's asking me 2 to the 5th. 2 to the 5th times 3 factorial times 5 factorial. And now what's going to happen is that we're going to have in the pattern created. Okay, so we have even subscripted amounts. So we have C of n, and we're going to have equal to -1 raised to the n over 2 C naught and what's going to happen here, so we have for the base 2, so we have 2 to the n minus 1, and this part, so we have so you got n over 2 factorial, and then you have followed by n over 2 plus 2 factorial. And once we let n be equal to 2k, so for C of n, okay, so we have -1 to the k, C naught, and we have all over, okay, so letting n be equal to 2k, so we have 2 to the 2k minus 1, and you have n over 2 factorial, so this will be k factorial and we have all over k plus 2 factorial, and we have in terms of the follow through. Okay, so again, just going back to what we have with y. Again, your x to the r1 was x squared. Okay, so letting n be equal to 2k. Let's see, let me back up here. So we have x to the n plus 2. Okay, so letting n be equal to 2k, so have the summation as k goes from 0 to infinity. In fact, so this is going to be a little bit ahead of myself, so that's going to be c of 2k. So I have c of 2k times x raised to the 2k plus 2 power. And if I draw out, okay, what I have in the constant, C naught, okay, so C naught times the summation, so you have k going from 0 to infinity, and it's going to have -1 to the k. And right now, so I'm going to switch the order. It's got -1 to the k, and I have all over k factorial times the quantity of k plus 2 factorial. But right now I have a mismatch between the degrees upon which x and 2 are going to be raised. Okay, but I can make a quick fix of this. Okay, but for right now, I have x to the 2k plus 2. And right now I have over 2 to the 2k minus 1. And I want to put this in terms of where the power is going to be at 2. Okay. And what I can do here is I can rewrite this for this 2 over 2 raised to 2k minus 1. Okay, so we have in this particular layout if my computer wants to die on me. Okay. So we got here. Okay, so I have x to the 2k plus 2 all over 2 to the 2k minus 1. But what I can do here is kind of working with the math on this one. Again, you have in the denominator, we got 2 raised to the 2k minus 1. And if I were to express what I have in terms of the 2k plus 2 degree, I can say I have 2 to the 2k plus 2 minus 3. Okay, so I have in this one, okay, so I have in the rewrite, so I have C naught, and I'll just say I have C naught over 2 to the negative 3. K equal to 0 to infinity. I have minus 1 to the k all over k factorial times k plus 2 factorial. And that's what we have in terms of the wrap on this one. Okay, so we have x, we have over 2. And again, this will be to the 2k plus 2 power. Okay, so in this particular part, I'm partitioning out 2 to the negative at the bottom, so to the right of the summation, divided by the 2 to the 2k plus 2 power. Okay, and just kind of mention we have for this part for C naught over 2 to the negative 3. Just kind of mention, okay, so if I had to get this like equal to 1, if C naught is 2 to the negative 3, okay, so your C naught would be a 1/8, but just for all intents and purposes, we'd say this is just going to be a constant, and a constant times the summation will be, okay, just a constant times the summation, and we have now taking what we have in this particular arrangement. So we have the decimal function at the first time. Okay, so you have in this one. Okay, so you have with the power at 2, so you have -1 to the k factorial, k plus p is going to be k plus 2 factorial. Got x over 2, 2k plus p is going to become 2k plus 2. And so we're going to have for the end result here, your Bessel function of the first kind, and that j of p of x, that's going to be j of 2 of x. Okay. All right, and now let me just kind of mention, if we look into Maple for just a moment. Okay, I'm just going into new worksheet mode, and we'll say that we have so we have the context panel and the toolbar set up. Okay, so again, if we're looking at solving an equation, I'll show you what I'm in here. So we go to Tools, Tutors, Differential Equations, ODE Analyzer, and say we had with the earlier equation. So we're going to go to Edit, Assist. Okay, so we're going to have so you're going to have x squared, x to the second, times, we have y with respect to x, the second order, so x squared times second order derivative of y with respect to x, and we have plus x times, we got assist y with respect to x of order 1, insert, and we have plus x squared times, okay, and now for the ODE analyzer, okay, for entering for y, you have not just y, but you had to put in y of x. Okay, so if I add this in, okay, so I add this in, we got done. And if we look at solving symbolically, okay, for the item of interest, okay, now this is this J naught x, okay, so that's the Bessel function of the first time. So you know, this is used to order 0, and this is the Bessel function of the second time. We're not going to worry with this one. Let's see. Okay, there we go. Now, see if I go back, okay, and the other equation, let's see, that was x squared minus 4. So what I'm going to do here is I have x squared minus 4 times y of x. Now if we look at solving symbolically, yeah, I'm recording it, so I'm gonna have it available. Okay, and so for what we have here, yeah, I wish there was there's a way of zooming in. It's okay. Okay, so again, we have with our general solution, okay, for the Bessel function. Again, this was the first time where we had to do the second order. We deal with the second time, but this is in the capacity of what we have with these equations. Okay, this is what you're going to have now. And then mention now regarding what we have with, say if I go back and let's say if I have, let's say, an initial condition, and we'll say that we have or say I have an initial condition. I think this one is going to work out. Okay, well, let's say if you have an initial condition, say you have y as 0.1. Say y is 0.1 is equal to 0.5. Now add this in, done, and I can solve symbolically. Okay, so just for the initial condition, I have y at 1/10 is equal to 0.5. Solve symbolically. Solve. Okay, so I have this expression, and to get this to show up, okay, I'm just going to go to quit. So I have this particular expression, and now if I'm looking at evaluating at a point, so I'm just going to highlight this, and where it says to evaluate at a point. Okay, now I will have x equal to 0.5. And I'm going to say that for C of 2. Now, C of 2 is a reference to the Bessel function on the second time, but we're just going to deal with just the first time. So just for that C of 2, just to get rid of the y of 2, I'm just going to make this one negligible. So I'm just going to set this one equal to 0. Okay. So you have in your result, you have in terms of the Bessel function of the first kind, and in terms of what the value will be. So if I can go to approximate and to about the nearest 10 decimal places. So for this, and say if y at 0.1 is equal to 1/2, it turns out that whenever x is at 0.5 or x at 1/2, your output, in this case your y or your Bessel function output, is going to be just over 12.25.